Alright, so our main goal for today is to talk about the calculations regarding solutions and concentration, but there's a few things we didn't quite get to yesterday we need to look at. So we remember from the double replacement reactions where we learned the yes or no solubility rules. We looked at the table to yes soluble or no it's not soluble. Yesterday we kind of looked at the chart where it shows the trends for solubility in relation to temperature. But now one last thing is how to predict when we make a certain change if solubility will increase or decrease. So the first example we'll look at are solids being dissolved in a liquid. That's the most common example. We have something we dissolve in a liquid that's most likely water. Okay? So for that situation, the solubility of most solids increases when temperature does what? Increases. Okay? I'm sorry. Okay. So most solids have a solubility that increases with increasing temperature. Is that always true? Now there was one example on the chart that didn't hold that statement to be correct. We'll learn in the equilibrium chapter why that's not always correct. But unless told otherwise, we can always assume that solubility for solids increases as temperature increases. Okay? If it is an exception, you'll be told that explicitly. So that relates to the amount that can be dissolved, just the total amount that can be dissolved in water. The next statement's about the rate at which it dissolves, how quickly it can be dissolved. So temperature changes how much we can dissolve. What changes how quickly the solid can dissolve?
Pressure.
Not really pressure.
How much you have?
Amount of the solid. Negative.
If you drop a bunch of salt in water and want it to dissolve faster, what are you going to do to it?
Stir
You stir it. Okay, so stirring or motion. Or if you have a giant salt crystal and you want it to dissolve faster, what are you going to do to it? Crush it up. So you're going to do what to the particle size? Increase or decrease the particle size? Decrease. So we can say it increases with decreased particle size. And we can control that most times. Okay? So if we're in the lab and we want to dissolve it quickly, we can crush up the solid. Okay? Now that has nothing to do with a total amount that can be dissolved. So if I have a 50-gram crystal or 50 grams of powdered sodium chloride, could they both dissolve in equal grams of water? Yeah, how it looks doesn't affect if it can or not. It does affect the rate at which it dissolves, which really doesn't matter for now, but in lab it will kind of matter for us. So then we can skip the next one. You know, at this point, hopefully, stirring, temperature, and particle size are the three things we can do to affect the solubility and rate of dissolution for something. So we know about solids dissolving in liquid. That's most common. We can skip the liquids portion. We aren't so worried about liquids dissolving in liquids. If you take organic chemistry, you'll talk a little bit more about that. What we're more concerned about is the gases portion for now, when a gas dissolves in a liquid. So where is the example of a gas being dissolved in a liquid that you've encountered? Where do you encounter that in your everyday life? Where?
Carbonation.
Everyday life.
Carbonation of your drinks, right? So Coke, Mountain Dew, Sprite are all carbonated. So that means what gas is dissolved in your liquid? Carbon dioxide, okay? So all the carbonated drinks you buy, when it starts fizzing or starts bubbling, that is what molecule being released from the solution? Carbon dioxide, okay? So if you leave a drink sitting out long enough, we say it gets flat, right? So that means all the carbon dioxide has left the solution, okay? So when it's sealed up, there's a lot of CO2 dissolved in the Coke or Sprite, whatever you drink. Then when you open it or you heat it, do something to it, all the carbonation leaves. So all these CO2 molecules leave the solution. So the rules for how much gas can dissolve in a liquid are kind of the opposite of solids. So we say for gases, the solubility decreases with an increase in temperature. So let's think about why that is. Okay, so if I draw a little container, I have a liquid, and I have some CO2 dissolved in the liquid. On a molecular level, what is the only difference in a solid and or a liquid and a gas? Excuse me. What's the difference in a liquid and a gas? Yeah, how fast they're moving. Okay, so as I increase temperature, they start moving more quickly, right? So eventually, if this CO2 starts moving fast enough, can it escape the liquid and become a gas again?
Yes.
Yeah. So does it make sense that if I increase the temperature of a liquid, I can dissolve fewer gas particles? Yeah, hopefully. Okay. So as you increase the temperature, the motion increases, then they're more likely to leave the solution. Okay. If it's very cold, are the molecules moving slowly or quickly? Slowly. So if they're moving very slowly, are they more likely or less likely to escape the liquid and become a gas? They're less likely. Okay. So when it gets colder, it's less likely to escape, which means you can dissolve more of the gas in the liquid. So that is the exact opposite of dealing with solids being dissolved in a liquid. When I put sodium chloride in water, am I super worried about sodium chloride becoming a gas and floating away? I'm not worried about that. Okay, so the temperature has the opposite effect there. The sodium chloride is not going to escape the solution and become a gas. Okay. Then, more importantly, in relation to your soft drinks, we can say the solubility of a gas increases with the pressure of gas above a solution. Okay, so as the pressure of gas above a solution increases, the solubility of a gas increases. So let's look at that. So if I draw another little container, and I have some water, I got to put a lid on this one. Why do I need a lid for this example? Yeah, you can't increase the pressure with a lid off of it. Okay. So now I have CO2 gas up above the liquid, and I'm trying to get the CO2 to dissolve in the water. So if I increase the pressure and add more and more CO2 up here, does it make sense that more CO2 can be forced into the liquid? Yeah. So as we increase the pressure of whatever gas I have above the liquid, I can dissolve more. Okay. So when you open your can of Coke, what does it do? Makes a little whoosh noise when the pressure decreases. Okay. So then, if you leave it sitting open for a while, all the CO2 goes where? Out into the air. Okay, because you decrease the pressure, and it's no longer forcing CO2 down into the liquid. Okay. Does that make sense? Okay. So then we can rewrite it another way there. So it says that increasing the temperature decreases the solubility of a gas. Same thing, just written backwards now. And we know that increasing the temperature only increases the kinetic energy of the particles and causes them to move more quickly. And potentially lets them jump out of the solution. Okay. Where's another place where you've encountered gas dissolved in a liquid other than your drinks? No. Think about what your lungs do. What are you taking in your lungs? Oxygen. How does it get around your body?
With water?
In the blood. Okay, so the blood's a liquid, mostly water. So it transports the carbon dioxide and oxygen around your body. Okay, the process is a little more complicated, but the same basic thing's going on. We're taking a gas, dissolving in the liquid, and transporting it around. Okay. So Henry's law is just a way that we, or who came up with this, a way that we have a statement or words to describe how the pressure affects the solubility of a gas. So it says the solubility of a gas is blank proportional to the partial pressure of a gas on the surface of the liquid. So if solubility increases as pressure increases, what kind of proportion is it? Correct. They are directly proportional. So that should be very logical. As you increase the pressure of the gas above a liquid, you can force more of the gas down inside the liquid. Okay? So then increasing pressure will increase the solubility, and decreasing pressure will decrease the solubility. So can you store your Coke or Mountain Dew on the counter for a week in an open container? No. Okay, once you let the pressure out and leave it open, the solubility is going to decrease and the CO2 is going to be lost to the air. Okay? So would there still potentially be CO2 dissolved in that liquid? Yeah, just not the amount that we like. Okay? Humans like when there's a lot of bubbles, and for there to be a lot of bubbles, you have to have a lot of pressure to force it down in there. The issue with that is, because we like the bubbles, we have to add so much that it immediately starts to dissipate into the air when we open it up. So if you ever watch your soft drink in a glass, you see the bubbles constantly forming and floating up to the top. That's just the CO2 that's dissolved in the solution, then becoming a gas and floating away into the air. Okay. Any questions about that? The solubility of solids or gases in a liquid. The main thing to remember is, as far as temperature goes, gases are the exact opposite. It's what you see with solids. So then one quick thing from the last chapter that we talked about before, we did the lab where we dissolved the salts in the water, and the temperature either went up or went down. So when we made the solutions, we either saw a temperature increase or decrease. So we call that the heat of solution or the enthalpy of solution. It's just the amount of energy we either gain or release when we dissolve a salt or dissolve something in water. Okay? So it's just the amount of energy absorbed or released. So we have two examples here. We have lithium chloride plus water yields lithium plus Cl minus plus 37 kilojoules. So what happened to that lithium chloride when it dissolved in water? It broke apart, but what's the word for that? What's the new word for it? Starts with the same letter. Not decomposed.
Dissolve.
When it dissolved, what did the salt?
D-I-S.
You said like every word around it.
Disassociated.
It disassociated. Okay. So lithium chloride dissociated in the water. It broke apart into Li plus Cl. So is energy a product or a reactant here? It's a product. It's after the arrow. So was energy absorbed or released? Released. So energy is released. So if energy is released, will the enthalpy change of solution have a negative or positive value? Negative. Negative is energy released. So a negative delta H tells me the process is endo or exothermic? Exothermic. Okay. So dissolving these salts does have an energy value associated with it. So if it is exothermic, is the water going to get hotter or cooler? The water's going to get hotter, okay? More hot, I guess. So the lithium chloride is going to release the energy. The water is going to absorb the energy. So the water would see an increase in temperature. So for this one, the dissociation of potassium iodide, is energy a reactant or a product? Reactant. So is energy absorbed or released? Absorbed. So would I see a positive or negative delta H? Positive. So endo or exo? Endothermic. So what kind of temperature change would I see with my water? Get cooler. It would be a negative temperature change. Okay. That's nothing new. Okay. Any questions about that? So now for what we want to talk about today. So today we're going to start talking about the concentrations of solutions. So what does concentration mean? What is that? It's just how much stuff I have dissolved in it, basically. Okay. So there's a definition typed out there for concentration. So we say it's to measure the amount of solute in a given amount of solvent or solution. So the good news is the calculations for concentration are very easy. The bad news is there's a bunch of different units for concentration. Okay. We'll look at two of them today and then a couple more later in the week. But there are many, many different units we can use to express concentration. The first unit for concentration is by far the most common though. So the first descriptor of concentration is molarity. So just based on the name, molarity is going to deal with the number of moles. So for once, the symbol makes sense to us. Molarity is represented with a capital M. Okay? So the definition of molarity is the number of moles of solute divided by the volume of solution in liters. So notice that says volume of solution. It does not say volume of solvent, right? So if in the salt water, or in the salt plus water example, the solute is salt, the solvent is water, the solution is the salt water mixed together, okay? So first let's write the formula, have we calculate it. What's the symbol for number of moles? N divided by liters of solution. So in calculating molarity, grams has to be converted to what? Moles. Milliliters has to be converted to liters. So let's think about this though. So let's say I want to make a solution with a molarity equal to 1, and I want to make 1 liter of solution. Okay? How many moles would I need? 1. The issue is, if I measure out 1 liter of solvent, so 1 liter of water, and then I add some salt to it, do I still have 1 liter of solution? No. When you add something to 1 liter, you get more than 1 liter, right? So it's important to note it says liters of solution, not liters of solvent. Okay? So we'll talk about that in a few minutes, how to deal with that. Just be aware of that for now. And the other unit we'll discuss today is molality. M-O-L-A-L-I-T-Y. Just to make it a little more confusing, they're very, very similar. So molarity is represented with a capital M. Molality is a lowercase m. Very similar definition though. Molality is the number of moles of solute divided by the kilograms of solvent. Okay? So this is kilograms of solvent, not kilograms of solution. So what's the solvent that we're always going to use for this class? Water. So there's something special about water that makes this a lot easier. 1 kilogram of water has what volume? 1 liter. Okay. So we can make a note off to the side. 1 liter is approximately 1 kilogram for water. Now in the future, if you use a different solvent, can you say 1 kilogram to 1 liter? No, that only works for water because the density is pretty close to 1 gram per milliliter. So would we expect the numbers for molality and molarity to be fairly similar as long as we're dealing with water? Yeah. The only difference will be this one looks at only the solvent, molality, whereas molarity looks at the whole solution. Okay? So to calculate lowercase m, I have n divided by kilograms of solvent. So molarity is by far the most common, but there's a couple of calculations we'll have to use molality for in a few days. So questions about that? So let's look at how to use molarity now. Let's turn over. So it says, how do you make a 0.5 capital M? What does capital M stand for? So it stands for molarity, but I read that as 0.5 molar. So if I ask you, what is the molarity? You don't say 0.5 molarity, you say 0.5 molar. Does that make sense? Okay. So what is the molarity? The molarity is 0.5 molar. Okay. Using a 1 liter flask. So here is a volumetric flask, we remember. And they come in different shapes and sizes, but they only come in the nice round numbers. So 50, 100, 250, 500, 1,000. Okay? And they're only good for measuring one volume. Right? This says 1,000. It has a line at 1,000. That's all it's good for. Okay? So I want to make this thing full of 0.5 molar sodium chloride solution. So the first step I got to do is to figure out what? Why do I need the molar mass of sodium chloride? So I need to find the number of moles of sodium chloride I need first, right? So what is my formula for molarity? So number of moles divided by liters. Do I have the number of moles? No. Do I have the molarity? Do I have the liters? Yes, so can I find the number of moles? So N equals 0.5 moles. Can I go to the balance and weigh out half a mole though? No, so I need to convert from moles to what? Grams. So we'll say step 1 is calculate number of grams. So it's going to be 2 steps. First calculate number of moles, then go from moles to grams. So can we skip that? You all handle that on your own? Go from moles to grams? Okay. So now I know the number of grams. I got to weigh out the number of grams, right? So weigh out proper number of grams. Now it's tempting next to go ahead and fill this thing up to 1,000. So if I fill this up to 1,000, I have exactly 1 liter, so I'm in great shape. But then if I add the salt in, am I still going to have exactly 1 liter? No. Is that an issue? Yes. How do I fix that? Yeah, add the salt here first. So put the salt in the flask. Okay. So then, if I fill it up to 1,000, once it dissolves, it's not going to be 1,000 anymore. So what's my next step going to be after I add the salt?
Weigh
No, I can't do that yet. I just want to put some in there. Fill it about half full. We'll just say fill halfway with water. And the reason I say fill halfway is because before I top it off to 1,000, I want to dissolve the salt. So I fill it up to about right here. Can I then dissolve the salt and then add the rest of the water? Yeah. So you add half the water, then you stir it. Can you use a glass stir rod to stir this very effectively? No. But based on how this is shaped, what can you very easily do? And just shake it around. Okay, just swirl it around. If that doesn't work very well, what's another tool we have to stir? You have a little magnetic stir bar. It's like a little pill. Drop it in there, put it on the magnet plate, it stirs forever. What is the issue with that? You've got to take it back out. It's hard to get back out. You can, but you have to. If you don't take it back out, when you fill it up to 1,000, is that really 1,000 milliliters? No, it's 1,000 milliliters including the little magnetic stir bar. Okay. So if you use the stir bar, just be sure you take it back out before you're done. Okay. So step 5 could be stir and dissolve. The one issue with swirling it is be sure you don't tap it on the lab bench. They're kind of fragile. So just swirl it around. You don't want to stick your finger in it and try and do this. If you get your finger stuck in it, I'm not going to be happy. I'm probably going to help you get it out. You're going to be on your own. Okay, so don't get your finger stuck in the volumetric flask. Everybody got that? No fingers being inserted in the flask. Yeah.
Does that mean somebody's fingers gotten stuck in there before?
I have gotten my finger stuck in it before. Yeah.
Oh, you have?
I have. Well, the issue is you stick it in there, and then your hand gets hot and it swells up, and anyway.
What you do?
Did you just break the thing?
I thought about it. It started hurting. I ran under cold water, my finger finally came out.
Oh.
I was not in a good mood that day. That was a long time ago, though.
I'll tell you, so there's a way to get it out.
Yeah, I thought about just breaking the thing, but I didn't. Anyway, so then after it's dissolved, what's the last step?
Or add the rest of
Yeah, just go ahead and fill it up to 1,000. Okay. So remember, you're going to put it on the lab bench. You want to bend over. You don't want to hold it up to your eyes because you can hold it level. So set it down, bend over, make sure the bottom of the curve is right on the line. Okay. Then, one last step we won't write down. If I top it off to 1,000, and I stick a pipette down in here and suck some out, am I going to get the salt solution? I'm going to get mostly water, right? Because if I just pour water on top, this top layer is mostly water. So what's your last step going to be? Go ahead and stir it. Now can you put the stir bar in without caring? Yeah. If we know there's 1,000, if we drop the stir bar in, it goes above 1,000. But do I care about that? I'm done measuring. So you can drop the stir bar in, let it stir, and you're in good shape, okay? Or you can put your thumb over it and do that. But that's tenths of speed also, I wouldn't advise that. So that is the proper way to make a solution of a certain molarity. The tempting thing to do is just measure out mass in grams, measure out the volume of water, and dump them together, okay? Can I do that making solutions of a certain molarity? No. If I was making a solution of a certain molality, could I just measure out the water, measure out the solid, stir them together and be happy? Yeah. Because do I care about the final volume of solution when I deal with molality? No, only molarity. Okay. So let's look at number one. So number one, I give you a volume, I give you a mass in grams, I ask you to calculate molarity. Can you do that? Yeah, convert from grams to moles. So then look down at, let's see, number three. Number three, you've got to convert milliliters to liters. And then, let's look at number 6 really quickly. So 6, I give you a reaction. What should your first instinct for number 6 be? Balance it. Then, if I give you a concentration and a volume of H3PO4, could you find the moles of H3PO4? Yes. Can you convert from moles of one thing to moles of a different thing using the balanced reaction? Yeah, then you can solve for grams. Okay. So go ahead and take 10 minutes and solve those 6 really quickly. And the answers are typed out accurate, so you should be in good shape.